Welcome to Module 3, which is about process synchronization and deadlocks. We had a discussion about process synchronization in class, right? You remember that example in which two different friends started a joint account and they tried to deposit some amount into the same joint account from two different branches almost simultaneously. And what happened? Unfortunately, the amount they deposited was not reflected correctly in the account, right? Because those two different deposit actions acted on the same data simultaneously. That was the issue there, right? So keeping that in mind, let us move on to module 3 and the details of this problem and its solution. So coming to process synchronization, these are the contents to be covered. To introduce critical section problem, we will see what is critical section problem and different solutions are there to solve this critical section problem. All those will be covered. There are both software based solution and hardware based solution. We will see both type of solutions and then we will examine different classical synchronization problem. What do you mean by classical synchronization problem? You remember that producer consumer problem, right? Yeah, producer. There are two different processes which are concurrent. That means they can execute simultaneously. And what was the other thing? They share a common shared memory, common buffer, right? What the purpose of the producer? Producer produce some items and it will put into that buffer and the consumer will consume those items. What's the significance of such a producer consumer problem? Yeah, lot of scenarios in a system can be depicted using this producer consumer problem. For example, that compiler assembler pair is typically a producer consumer problem, right? Compiler produce some assembly code which is consumed by the assembler, like that assembler loader. That's another consumer producer consumer pair, right? So any issues that is faced by these type of system environment can be easily depicted using this producer consumer problem. And if we can test some solutions to this producer consumer problem. So if that solution solve the issues in a producer consumer problem, that we can easily apply to the system also. Right? So we will see different classical synchronization problem. Then we will see different tools that can be used to solve this process synchronization problems. So before moving into this process synchronization problem, let us see some points to be considered while discussing these problems. First one is that in a system, the processes can be either independent or cooperative. Two types of processes are there in a system. It can be either independent or cooperating. What do you mean by cooperating processes? Cooperating processes can affect or be affected by other processes, including sharing data. So we can say that two different processes are cooperating if one execution of one process affect or be affected by the execution of another process. Either maybe because they share some common data, updating table or common file like that. Whatever may be the reason, if two processes may be affected by each other, we can call those processes as cooperating processes. Otherwise, they are independent. So in the case of independent processes, they can execute in simultaneous mode without any issues, right? But in a cooperating environment, there can be issues. Another thing is that processes can execute concurrently or in parallel. Okay, we will see what is concurrent execution and what is parallel execution. So in case of concurrent execution, two different processes are in execution simultaneously, but we have only one CPU or one CPU core. In that case, what happens? The CPU scheduler switches rapidly between these two processes. Not just two, many processes may be there in concurrent execution. So the CPU will be switched rapidly between all those processes. Okay. This means that one process may only partially complete its execution before another process is scheduled. So all those concurrent processes may execute in an interleaved manner. Okay, CPUs will switches among these processes before completing each process. In a partial complete stage, it will switch into another process. That is the major challenge here in a concurrent execution environment. That means a process may be interrupted at any point in its instruction stream, and the processing core, that the CPU, may be assigned to execute instructions of another process. Okay. So, whereas in case of parallel execution means two different processes are in execution at the same time. That means definitely there should be multiple CPUs, multiple CPU cores may be there. In that case, two different concurrent processes can execute at the same moment. That is parallel execution. Okay, two types of environment. Either concurrent execution in which two different processes executes simultaneously, but we have only one CPU, so the CPU will switch rapidly between these processes. And the second one is parallel execution. Two different processes execute exactly in the same time because we have two different processing cores, two different CPUs. It need not limit to just two, but multiple processes can be in execution simultaneously. And concurrent or parallel execution can contribute to issues involving the integrity of data. That is the issue we have to consider here. So if the execution is in parallel mode or in concurrent mode, there can be issues. Okay. So concurrent access to shared data may result in data inconsistency. You remember that bank account, the amount deposited was not reflected correctly, right? That is an example for data inconsistency. So maintaining data consistency requires mechanism to ensure the orderly execution. So we should ensure that these two different processes which operate on the same data, there should be some order in which these two processes should be executed to ensure that data is consistent. So how we can insist such an order? That is the question. That is what you mean by process synchronization. So we will see such an example that producer consumer problem. We had a solution for producer consumer problem, right? Producer code and consumer code. And the first code was a major limitation was that buffer was not filled fully, right? Always if the buffer capacity was n, at most n minus buffer can be utilized by this producer consumer problem, and we try to modify that so that all the buffers can be utilized, right? We included a count variable, right? So remember that solution for producer consumer problem. We will see that code also. Solution to the consumer producer problem that fills all the buffers. Such a solution we can take as a scenario to illustrate that there are issues and that should be solved. We had included an integer count that keeps track of the number of full buffers. How many buffers are full now? We can keep track using this count variable. Initially that count will be set to 0, and whenever a producer produces an item, that count value will be incremented by the producer, and whenever the consumer consumes one item from the buffer, that count variable will be decremented. Now coming to the producer consumer problem, the modified version which include the solution that all the n buffers can be utilized for producer consumer transaction, right? Yeah. So remember that producer and consumer are actually two concurrent processes that may execute simultaneously, or maybe in an interleaved manner these two processes can execute, and they are cooperative in nature. That means they share something in common. Here they share a common buffer, right? Yeah. And these producer and consumer works forever in the system. That is why this code is put in a while loop, infinite while loop, right? While true, producer will work forever, like that consumer also work forever in the system. So what the producer will do, after producing an item, it will check whether all the buffers in the systems are full. If so, the producer have to wait. So count indicates the number of full buffers in the system, right? Yeah. So it will compare the count with maximum size of the buffer. If they are equal, that means the buffers are full now. Producer how to wait. So it will wait using this semicolon. You can see here, right? It will wait until some of the buffers become empty. Yeah. Otherwise what the producer can do, it can put the item into some buffer. Which buffer? We have two different pointers, right? In and out. In always points to the first empty buffer. Out always points to the first full buffer. So first empty location will be pointed by in. So into that location we can put the item produced by the producer. So this is a step to be followed. Buffer in is equal to next produced. After that, in should be updated. So next time in should point to the next empty location, right? Yeah. So and in should be incremented. Since we are using a circular queue, the modulo operator should be applied here. Then update the count. Now we have put one more item into the buffer. Now the number of full buffers is incremented. So just to reflect that, count should be incremented by the producer. This is about producer code. Like that we have the consumer code also. That is also an infinite process, right? While true. What the consumer have to do first? Before consuming an item, it will check whether the buffers are empty now. If all the buffers are empty, it should wait, right? So that is the first condition. If the count value is 0 means there is no items in the buffer, it have to wait, do nothing and wait in the while loop. Otherwise what it can do, it can fetch an item, can read an item from the buffer. Which item? The item pointed by the out, right? Out is the pointer which points to the first full buffer location. That item can be fetched or read by this consumer. It will fetch into this variable next consumed. Then it can update the out pointer. Out should point to the next full buffer. So out also incremented by 1 and one item is removed from the buffer, right? So count should be decremented to reflect the same. So count is decremented here. This is how consumer works. And the thing is that producer and consumer works in parallel. We don't know in which order these two processes are executed. Their instructions are executed in interleaved manner. That is the issue here. Now let us see if these two processes execute simultaneously or concurrently, what issue comes. So that is actually called race condition. We will first illustrate the corresponding issue, then we will move on to the standard definition. So count plus plus by the producer and count minus minus by the consumer, right? These two operations act on the same variable count, right? That is a single variable shared by consumer and producer. And there is a chance that both producer and consumer may execute those instructions simultaneously. Consumer may execute count minus minus at the same moment. Producer may execute count plus plus. Okay. So even though we are saying this count plus plus as a single instruction, when we execute in a system, it should be broken into micro level instruction, right? We cannot directly execute memory variable updation. So if you want to execute this count plus plus, that should be broken into this micro level instruction. First, count is actually memory variable, right? Its value should be brought into some register, say register 1. Then from there, it should be incremented. Register value is incremented by 1. Then write back that register value into count. These two micro instructions complete the single count plus plus instruction, right? So like that, in case of consumer also, if the consumer execute count minus minus, it cannot be executed in a single step, right? First, the value of the count should be read into some other register, say register 2. Then decrement the value in the register 2, write back that new value into count variable. To these three instructions together accomplish count minus minus. Okay. And the thing is that although the producer and consumer routines shown above are correct separately, they may not function correctly when executed concurrently. If we look into this 3 steps together, this is correct, right? This is count plus plus. Definitely it works correctly. And count minus minus also, as a single unit, we can see that everything works properly. It just decrement the value of the count by 1. But the thing is that if these two processes, both producer and consumer, work together in parallel, they may not work correctly. Okay, we will see an example for that. Suppose the initial value of the count is 5 and this is the order of execution. First, the producer execute register 1 is equal to count. Okay, first instruction is executed by this producer, and the second turn is also for the producer. So producer execute register 1 is equal to register 1 plus 1. That is also done. So initial value was 5. Now the value inside the register 1 is 6. It's okay. But unfortunately, after this instruction, what happened? The CPU switched it back into consumer. Now the execution proceed with the consumer. Consumer execute its first instruction, that is register 2 is equal to count, that is executed. So initial value of the count itself is there in the count, right? That was 5, that is fetched by register 2. Then again it's turn for consumer. Consumer executes the second instruction, that is register 2 is equal to register 2 minus 1, that is register 2 value now is 4, right? After that again the CPU switches back into producer. Producer execute its third instruction, count is equal to register 1. Count value now is updated with register 1 value, that is 6 again, right? And finally the execution proceed with consumer. Consumer execute this instruction, count is equal to register 2. Register 2 value, which was actually 4, that is updated into count. Actually, if these two process, that is consumer and producer, executes in the correct way, one updation, one increment and one decrement by these two processes. So the initial value should be as such, right? After executing these two processes once, the value of the count should be 5 itself. But what happened here, because these two processes worked in an interleaved manner, either the value will be 6 or 4 based on how these two processes gets its turns. Since here the last turn was for the consumer, the value was 4, value written into count is 4. If last transfer was for the producer, the final value would be 6 in the count, right? So that is actually data inconsistency. The value should be 5, but instead of that, because of interleaved execution of producer and consumer, the value could be either 4 or 6, right? This situation is called a race condition. Okay, so let us define what is race condition. We would arrive at this incorrect state because we allowed both processes to manipulate the variable count concurrently, right? The same value or same variable count was manipulated by both producer and consumer simultaneously. That was the reason for this inconsistency. So let us formally define this race condition. Several processes access and manipulate the same data concurrently, and the outcome of the execution depends on the particular order in which the access takes place, is called a race condition. So here in our example, last two instructions, right? Yeah, that is S5 and S4 and S5, right? The outcome of our value of count, that purely depends on which one was executed last. If it is S5, the count is 4. If it is S4, the count is 6. And the actual value is supposed to be 5 itself, right? So that is the definition. Several processes access and manipulate the same data concurrently, and the outcome of the execution depends on the particular order in which the access takes place, is called a race condition. So how we can guard against this race condition? We need to ensure that only one process at a time can be manipulating a variable counter. So the solution, whatever may be the solution, the thing is that if a particular process is manipulating that common data, no other process should be allowed to intrude or interrupt in between. Let the first process complete its execution on that shared data. Only after that, any other process should be allowed to access or modify the same data. Okay. So this is called synchronization. There should be some mechanism to ensure that different process execute or update or modify a common data with a specific order. Okay. So keeping in that mind, let us define what is critical section problem. So we have a set of processes. In case of producer-consumer problem, we have seen just two processes, right? But in case of a system, there can be n different processes. N processes, they are named as P0, P1, etc. up to Pn minus 1. And each process has a segment of code called the critical section, in which the process may be changing common variables, updating a table, writing a file, and so on. So the thing is that n processes are there, and these n processes are concurrent in nature, and they have a common data to be manipulated. Maybe some common variables, memory variables, or some table database may be there, or some files may be written by different processes. And so identify the code segment. Okay. So in case of producer and consumer, that count plus plus in the producer or count minus minus in the consumer, that is a segment of code that modify the common data, right? Like that, for any process which has a segment of code called critical section. So that code segment inside a process which modify the common data, that code segment is called critical section. So identify that critical section of every process. The important feature of the system is that when one process is executing in its critical section, no other process is allowed to execute in its critical section. That is the condition here. For example, in case of producer and consumer, if producer is working on count plus plus, no matter how many micro level instructions are there, if producer is executing count plus plus, never the consumer is allowed to execute count minus minus. Only after finishing all the three steps of count plus plus, consumer is allowed to execute. Okay, that is the condition here. That means when one process is executing in its critical section, no other process is allowed to execute in its critical section. That is a thing to be ensured by the operating system. So let us define this critical section problem. Critical section problem is to design a protocol that the processes can use to cooperate. So we have to ensure implement some protocols so that if we are using that protocol in the system, never two different processes will create some inconsistency in data manipulation. Okay. So each process must request permission to enter its critical section. So what we are doing actually is we are ensuring a locking mechanism. You can think about a locker system in a bank, right? Only one person will be allowed to enter into a locker room, right? So you will be provided with a key. After finishing its transaction, the key will be released so that some other person can enter into locker room, right? Like that, here also, if a particular process want to enter or execute its critical session, it should get permission from the operating system. Can I execute the critical session? That is actually locking mechanism. If I am getting the key for entering into critical session, I can do the critical session. So while I am doing my critical section, key is with me. I am locking my entering or locking the corresponding data so that no other process will enter into its critical session. Only after finishing all the transaction into this common data, I will release the key. I will unlock the corresponding data and will release the key so that some other process can enter into its critical section. So that is what you mean by request permission to enter. We will see the corresponding code. And the section of code implementing this request, can I get into that question, that acquiring the lock? That section is called entry section. And after finishing my critical session, what I will do, I will release the lock. I will unlock the corresponding data and I will release the lock. Okay, that section of code is called exit section. And after releasing my lock, I can continue with the remainder of my code, right? And that is called reminder section. So we will divide the entire process into different code segments. So if we analyze any process to ensure the synchronized execution, we have to divide this entire code into different parts, and we can picturize any process in these two or different sections of a code like this. Okay, so any process we can think of working an infinite loop, like producer and consumer work forever, right? Like that, any process, it works forever in the system. So we are including those code in a infinite while loop. So any code, before entering into critical session, we should include some code that is called entry section. Entry section, if the entry section is successful, the critical section can be executed. After completing the critical section, an exit section should be executed so that the lock is released so that some other process can enter. After releasing the lock, the process can continue with its reminder section. So like this, any process will be structured.